This week we're going to look at Portland cement concrete and a couple mixed design considerations when batching a Portland cement concrete. So the ingredients for traditional Portland cement concrete are pretty basic. We have aggregates, both coarse and fine. That's what we've been mainly talking about so far this semester. Remember, the coarse aggregates are your gravel or potentially crushed manufactured rock, and your fine aggregates is your sand. We have a cement paste, or actually I should probably say cement powder. We have water, which is used to make the paste. And then I actually call air an ingredient in concrete, because air, when desired, is intentional and designed for and added by means of an admixture. And there are more admixtures than just an air entraining admixture. Not all of them are always necessary, so that's why I kind of say admixtures if necessary. So if we look at the individual ingredients of concrete on a volume basis, this diagram out of the Portland Cement Association's design manual kind of shows that by far aggregates take up the majority of voluming, and because they're what provide the strength of concrete, and primarily strength is the property that we most care about with concrete. The cement, there 7 to 15% is the binding agent, really the glue, and air has a special purpose, a special application in concrete, and we'll kind of talk about that a little bit this week, but more so in future weeks. So the definition of cement is any material that's used as a binding paste, and in the construction industry, the two most common that you'll encounter are Portland cement and asphalt cement. And cement has kind of become that generic word, ubiquitous with Portland concrete, but like Kleenex, right? Kleenex is just one type of tissue, but we use the word Kleenex to refer to any generic tissue. We use the word cement more often than not to mean Portland cement concrete, but really that's an incorrect application of the word, where cement is just any generic binding paste. So some old historical traditional cements have been mud and straw, where straw actually kind of served as the aggregate in a sense to provide a little bit of structure to those building units. Adobe, which is clay, and we, as you recall from soils class, when dry, clay is an incredibly strong material. It's stronger than rock, but the problem is you can't always guarantee that it will remain dry. And then gypsum. Gypsum is actually an ingredient of Portland cement, and it has a special unique purpose we'll talk about here in a couple slides. But that's also still common for sound and temperature insulation in residential homes as a cementing material. And just a real brief history. Portland cement came about in the mid-19th century. Gentleman Joseph Abston combined limestone and clay and tried to, I guess, patent or keep his ingredients mysterious by claiming that he was adding secret salts, and that always makes me think of Marvel Mystery Oil, that mechanic in a bottle you can buy at Walmart for $6 or $7. The name has nothing to do with locale or geography. It became known as Portland cement because the finished product remembered the desirable Portland limestone from the Portland region of United Kingdom. So today's Portland cement concrete, it's made up of, like we said, the cement, the water, and the air, and then the aggregates. And the cement and the water and the air are um, designed based on a ratio. So we're comparing two ingredients and maintaining a ratio. As one increases, the other decreases. And you can see the ratio is water divided by cement. So if we're needing to add more cement to that mixture, by definition, the water will have to increase as well to maintain the proper ratio for the desired paste. Now, sand and stone, right, the coarse and the fine aggregates, they're designed based on a grading analysis. The grading, it, as you know, we've talked about for a year now, earlier in the semester and also back in the soils class, is just based on the segregation of mineral particles based on size. So depending on the gravel sample that is being used for this particular concrete, depending on whatever gravel pit this material is coming from, the gradation analysis determines how much of the particular coarse and fine aggregate is used. So there's three primary factors to take into account with Portland cement concrete mix design. We have strength, and that's the compressive strength, and this is the primary property that we generally care about with concrete. We want concrete to be able to resist compressive force. So when force is applied from the top, if it's resting on a foundation, it is also by default receiving force from the bottom, and we need the concrete to resist that force without breaking. Durability is a concrete's ability to withstand environmental conditions. In Montana, we primarily mean freeze and thaw action when that concrete is exposed to water. So how able is that concrete to withstand basically mechanical breakdown when water gets into it and freezes and wants to expand. And then workability. Workability is the only property we care about that's not attributed to the final product, right? So how easy is it going to be to work this concrete into whatever form or mold we need it to fit into? We can add certain things like plasticizers or admixtures to make it more workable, but as you'll see here in a couple slides, increasing workability can have a tendency to decrease the other two properties, strength and durability. So of those ingredients that we put into a mixture to make ultimately what we're going to call Portland cement concrete, the Portland cement, right, the powder, is the most expensive ingredient. So we want to understand the design considerations and minimize it while still getting the required strength. Right? We want to minimize the expensive materials, but maximize the properties that we want to get out of that concrete, and that's effective mix design. That's honestly the goal of any engineering, is achieving the desired result with the least cost and effort required. So I just want to take a step back away from concrete for a second and look at the old traditional triangle regarding project management. And the goal of project management is to balance time, cost, and quality on any product or any project. And what's unique about these three variables is you can't optimize you can't maximize all three. You cannot deliver a project fast and on time, cheap and under budget, and expect to have high quality, right? If you maximize these two, the third property suffers. Similarly, if you maximize quality and you maximize cost, it's going to take a lot longer to do. So you're sacrificing time for the sake of quality and money. And this is the challenge of any project manager, is where do we throw our resources, right? What do we want to maximize? And ultimately that answer comes from the goals of your client. So we can look at concrete mix design kind of the same way. We have three variables, or three properties, excuse me, that we're trying to achieve: strength, durability, and workability. And the goal of an effective mix design is to effectively optimize all three while not sacrificing any. We can't maximize all three, right? We cannot maximize strength and durability, because if we do, we're going to have a very dry, a very stout concrete that's not very workable at all. And we can't have extremely good workability, because that means essentially we're adding more water, right? We're jeopardizing the water to cement ratio, and we're sacrificing strength. So the ingredients of Portland cement, this tests the limits of my chemistry uh, skills, so I'm not going to spend a whole lot of time here. But by far the most prominent ingredient in Portland cement is lime, a source of lime. Traditionally around here it's limestone, because that's what we have available in Montana. You also have silica sources, aluminum or alumina, and an iron oxide to produce the hydration reaction necessary. We do have cement manufacturing plants located nearby. We've got the Trident plant over by Three Forks in Gallatin County, and we have the Ash Grove plant up just before Helena, up there in Montana City. And the reason they're located there, again, is because of the local geology. There's extremely good sources of limestone in this part of Montana. You know, if you've ever gone to the Lewis and Clark Caverns, you know, that's the effect of water acting on a limestone substrate. So a real brief description of the process to produce the Portland cement powder. This is covered in much more detail in the readings this week, but Portland cement is manufactured by grinding up those four materials, right? The lime, the silica, the alumina, and the iron oxide, and mixing them into a slurry. So a slurry is just a powder with water added to make kind of a thick soupy mix. So that slurry is then poured into a kiln, which is a giant rotating tube, a furnace, and that furnace bakes the slurry into a product called clinker. Clinker we're going to see a picture of here, I believe. Clinker is just like large BBs, large pellets. It looks like aggregates, it looks like gravel, but it's dried up chunks of that slurry. That slurry, or I'm sorry, that clinker is then ground up and mixed with gypsum powder, to produce the Portland cement powder. This is a picture of the cement production facility in Montana City. This is the input end where the raw materials go. This is the kiln, right? That big rotating drum. They're impressive. They're about 300 feet long from end to end, and the diameter, they're about 10 to 12 feet in diameter. The heat is just amazing when you walk down alongside one of these kilns. It's an impressive production. So the desired properties of Portland cement, right? Um, we can vary the ingredients, vary the amounts of lime, silica, iron oxide, to deliver different properties when it goes through the curing process, when we're making the concrete product. So the rate of hardening, right? How fast do we want the cure to take place from when it's in a liquid plastic workable phase to the hard final phase? And if you've got a long delivery time, say you're pouring bridge piers or highway slabs in eastern Montana, and the nearest cement plant or concrete plant is 3 hours away, you're going to need that concrete to survive a pretty long time in the truck. So you want to slow down the rate of hardening. The amount of heat generated during the curing process is a property, and a large massive structure like the Hoover Dam is that classic example, produced a tremendous amount of heat. So you want to minimize the heat produced, so you don't jeopardize the final product during that curing process. You can use a low heat um, Portland cement. And then also the resistance to chemical attack. So if your final product is going to be exposed to deicers like concrete highways or potentially high sulfate groundwater on house foundations or septic tanks that are underground, you might want to have a property resistant to chemical attack of your Portland cement. In order for that Portland cement to set or cure or harden, right, you need to add water into the concrete mix. So about 25% of the mass of the cement is required. That's how much water we need to add. So that's not very much water. That's the bare minimum just to accelerate the hydration process, or not even accelerate it, but initiate the hydration process. The more water you add, the more workable your concrete's going to be. So there's that balance of ingredients. And the hydration is that chemical reaction, just like a hand warmer, if you've ever used those in the wintertime. That byproduct of the hydration process is heat. So we want the hardening and the strength gains through the hydration process. We don't want the heat. So we need to either dissipate it or minimize it. And Portland cement reacts with the water, right? Creates the hydration process thanks to the iron ingredient in the Portland cement powder. But the gypsum is kind of there to act as a governor almost. When we add gypsum to a concrete, to the Portland cement powder, it's there to kind of neutralize the hydration process, and the gypsum will take some of that water and deny it access to the cement, and that slows the rate of hydration. So there's how we're trying to create a slow hydrating or a slow hardening concrete, is through the use of gypsum powder. Hydration gives concrete its strength and occurs over time as long as water is present, and that's key. If we can keep that concrete moist, hydration will continue to go, or to continue to react, and strength will continue to build. In theory, concrete never truly dries out. If you could maintain a seal on any concrete product for an indefinite amount of time, in theory it would never fully dry out, and it would always continue to cure and gain strength. Now you can see this is a table or a chart that shows the typical strength times. We have time on the bottom here. These are units of days, and we have strength on the vertical axis here, and these look like they are thousands of pounds per square inch, or maybe hundreds of pounds per square inch. So 2,500 psi, 5,000 psi, 7,500 psi, and so on. And as you can see, at day 0, right, the day you pour your concrete, the day you mix it up, it has no strength, right, because it's workable, it's plastic. And then at day 3, we've started to gain some strength already. So we're already up to a couple thousand psi. And your strength gains continue to really build over a short period of time. 7 is the typical day where you create your first strength break tests. 28 days, so 4 weeks, is the typical design strength. So we want our concrete to achieve the ultimate design strength goals after 28 days. But as you can see, strength will continue to grow as time continues to go on, so long as your concrete stays moist. But 28 days is kind of that magic break period where you don't really start to gain a whole lot more strength over a lot more days. So that's the sweet spot. That's where you've maximized your gains, your return. So how do you keep it moist? How do you keep it in a moist cured environment? Well, one is to keep it wet, right? And this was a slab I saw poured a couple summers ago, and I was riding my bike down the road and saw this sprinkler system just watering no grass. And I got a little closer, and sure enough, that was an effective means of keeping that concrete moist in a hot summer month, is to literally just water it overnight and keep water on it. Another way is to keep your water from freezing. So if you pour concrete in the wintertime, that water wants to freeze just like the snow and the ice and the puddles. So the second water freezes, it's no longer liquid water anymore, and that also denies it the ability to contribute to the hydration process in concrete. So you have to keep water present, but you also have to keep water liquid. So you can use, these are insulating blankets, and this was a sidewalk we poured in Butte a couple summers ago as part of a class project for some habitat homes. So when concrete dries, hydration stops. And when hydration stops, your strength gains stop as well. So the longer you can keep that moisture present and liquid, the more strength you're going to get out of your concrete. As the concrete cures, it's inevitable you're going to lose some moisture, and that will cause a shrinking effect on your product, and you can expect concrete to shrink approximately 3/4 of an inch for every 100 linear feet of product. So this is a problem because concrete is not a flexible material. Concrete is going to be rigid, it's going to be strong, and it's going to be resistant to change, both flexural and compressive change. So you deal with this by, one, controlling that rate of drying, and two, forcing it to fail where you want it to fail. And we do that with joints and saw cuts. And the traditional example is in a sidewalk, right? So down here in the bottom picture, you know that concrete sidewalk will crack eventually somewhere. So you force it to crack where you want it to. You put in a saw cut, it's going to crack right there, and that will relieve the pressure and maintain the integrity of the slabs away from that saw cut where you don't want any failure to occur. And this upper picture, this is that same sidewalk we were pouring as for the class project, and you can see here Jim is laying out every 5 or 6 feet locations to perform not the saw cuts, where actually this is still a moist plastic phase, so we're just going to lay in an edge and create a seam without needing to saw cut a final product. So types of Portland cement. Remember, Portland cement is just one ingredient of the whole concrete mix, and Portland is that powder we think of. You can buy it in a sack at any hardware store. So we have 5 types, and your readings are going to go into these in a little more detail. But type 1 is what you buy off the shelf at Home Depot. It's normal. It's a normal cement. I'm sorry, normal Portland cement, sack cement. Types 2 and 5 are resistance to sulfates in the groundwater. Those are those chemical attacks, right? The de-icing materials, the high sulfate groundwater. Type 2 is moderate resistance. Type 5 is high resistance. Type 3 is a high early strength concrete. And type 4 is a low heat producing, low heat producing cement, not concrete. When you see an A modifier added to the end of one of these types, it just means that that is a cement intended to be used with air entraining outcomes. So type 1A means normal type cement with air entraining. So we think back to that triangle, strength, durability, workability, when you want to maximize one, the other two are going to suffer. And what I'd like you to think about this week as you go through the readings is what happens to those other two when you maximize one, right? If we're going to maximize strength with our ingredients, what's going to happen to the durability and the workability? What if we want to maximize our durability, because we're going to be exposed to a lot of severe environmental conditions, a lot of freeze thaw, a lot of cold weather? What's going to happen to the strength and the workability? And same if you're a worker, right, a tradesman, and you're the responsible for working with the concrete as it's delivered on site, you care about workability. You want it easy to work with. Well, you might not care about the strength and the durability of the final product, but ultimately, potentially lives of people will be dependent on those two properties. So what happens to them when you ask the concrete delivery truck to add another couple gallons of water because you want it more workable? You can balance those sacrifices or minimize those sacrifices through the use of what we call concrete admixtures. And these are special chemicals that you add into the concrete mix that enhance one of those properties without sacrificing the others. And we're going to spend an entire week talking about chemical admixtures in the future. And just some little research into admixtures. I learned that some early admixtures, kind of interesting, animal fat and milk were used long ago to improve workability. And it's thought that blood was actually used as an admixture. And the idea here is that the hemoglobin in the blood, right, the oxygen binding capacity of your blood, it's what helps deliver oxygen to your muscles and organs as your blood goes through your veins. It's the hemoglobin in the blood. It was thought that the hemoglobin worked as an air training and actually improved the durability in freeze thaw conditions.